So I'd like to again acknowledge those people who helped us put this information together. In addition to my colleagues in the UN-GGCE, also a range of people from the USA, Mexico, Australia, Germany, and Canada provided input when Ryan made a call out to get information for all these sessions. Different people in different sessions that you'll see acknowledged at the bottom came back to Ryan and said, here you go, you can use our data, you can use our information. And then we used all those different data sets to help weave it together and tell a story. So that's how all this information came together. It wasn't just from us in the center, we took in all the knowledge from other people as well. So this is a summary that I put together that looks at the problems and the potential solutions associated with joining land and sea data. And as you know about me now, I like to try and tell you the answer at the front. Don't save the answer for the end, put the answer at the front. And the answer is to make sure that we're using a geoid model. So if you're from a country where your land and sea boundaries, that littoral zone is a challenge and something you need to be working on, this is an extra advice for you to let you know about the importance of having a good geoid model for your country, because it is the link between your offshore and your onshore resources. The geoid model can then be used as a surface that you can link to many other surfaces. So you can create surfaces that go between the geoid and the ellipsoid, mean sea level, and then offshore datums like highest astronomical tide, lowest astronomical tide, which is often the chart datum for many of the ports, and things like mean dynamic topography. The benefits of using this approach is that, as we talked about the other day, the geoid is a physical height surface, so water will always flow downhill on that surface. It also exists offshore and onshore, and there's no other surface that we can use in geodesy that meets all of those criteria. The challenges associated with the use of the geoid model, though, is, as we saw across Africa, these absolute models, these gravity models, are about accurate to about 15 to 20 centimeters. So that can be a limitation. Remember, relative positioning, you might get better than this, but in an absolute sense, it's not as accurate as it could be. So this is where you need the local or regional geoid models. And for that, you need things like airborne gravity data and terrestrial gravity data. And that can be expensive. You can also develop hydroid models. So these are offshore models that give you the difference in height between the ellipsoid, the geoid, and sea level. And these become very useful particularly for the shipping and maritime industries. So let's have a look at this diagram. And you can just see how easy geodesy is, right? Particularly when you're talking about height. Look at all the different types. I've simplified this as best I can. And my advice would be, let's start with the green ones. So the green ones are our geodetic datums. And you can see at the bottom is the ellipsoid. And then if you go up, you can see the geoid. And the geoid, when we get offshore, the geoid is closely approximated to mean sea level. But then there's a difference between that and chart datum, which might be the lowest astronomical tide, which is the red one. That's a hydrographic datum. And then you also have the current water level. And that changes over time. So it needs to be a dynamic model to deal with the changes in tides over time if you're going to safely guide this ship coming in and out of the port. And you can see we're using tide gauges and GNSS information to collect all this data and provide real-time positioning capabilities to the shipping industry. The land side is something that most of you are more familiar with. It's updated on my screen. I'm just waiting for it to update on the screen that you can see. There we go. It's not liking that slide. I'll jump through to this one. So here you can see where that the sea component is linked with the land component. And the land component, you can see, is the piece in purple on the right-hand side. That's our land datum. That would be your leveling datum, which it might have been set up to approximate mean sea level, which is what many of the countries that I know about throughout Africa use. They try and use something linked to sea level if you're around the coastline. And then that wavy green line on the right-hand side is the geoid model. So as you can see, as you come further from offshore, that geoid model is going to change and deviate away from what was close to mean sea level, because the geoid is affected by the terrain, by the land around you and mountains and things like that. So it's going to move up and down depending on the changes in the Earth's gravity field onshore. And then you have your orthometric heights, which is the link between the land datum and the geoid model. The land datum and whatever your infrastructure is. So here we're looking at houses, and you've got orthometric heights, which is the height of that house with respect to the land datum. I've now got a practical example for you. If I can get the screen to update. Here we go. There we go. So this is an example from the Pacific Islands countries. So this is where I've done most of my work when it comes to joining land and sea information in my previous role with the Australian government. And this is a region where Australia has been supporting 13 Pacific Island countries to measure, record and analyse the long-term sea level trend and land motion over the last 25 years. The sea level data is collected continuously at one or two different tide gauges in each of the 13 Pacific Island countries, and the land motion data is collected continuously at GNSS cause stations on each of the 13 Pacific Island countries. And then the height difference between the tide gauge and the GNSS station is observed with leveling about every 18 months. So a tide gauge, if you think about it, a tide gauge on its own can't differentiate between changes in sea level height and movement of the land. If a tide gauge is observing 5 millimeters a year in sea level rise, we are not able to distinguish whether that's because the land is subsiding or because the sea level is rising or because it's some combination of both. So to distinguish between relative and absolute sea level variation from the tide gauge data, it's necessary to know the movement of the tide gauge in an absolute frame of reference. And that's what Geodesy gives us. That's what we can do with GPS. And the absolute frame of reference we use is what we use for GPS, the center of the mass of the Earth. So in the Pacific Island countries, that's why these GNSS sites were installed. The main purpose of them was to help understand land motion, so we could differentiate between land motion and sea level rise in these countries. So a GNSS station was installed within about 5 kilometers of each tide gauge. And at these GNSS sites, it's possible to determine the change in the height of the land over time. And then what we do is we link these techniques together. So you can see up the top on the left, we've got our GNSS site. That's our cause station that's running. And then down on the far right-hand side, we have our tide gauge. And then every 18 months, a team within SPC, which is the Secretariat of the Pacific Community, it's a regional body within the Pacific, they send their surveying staff out and do the leveling in between the GNSS and the tide gauge to create that connection between them. And effectively, what we're trying to do is work out, is the land underneath the GNSS site and the land connected to the tide gauge moving consistently over time? Or is there something localized in the movement of the site? Let's have a look at an example from Samoa. And what we can see here is an earthquake that occurred in September of 2009 in Samoa. And you can see that this is our GNSS height information you can see that the land was relatively stable for a long period of time. Then the earthquake occurred. And then since the earthquake occurred, the land has continued to subside at that point. So the land connected to the GNSS is continuing to go down over time. What we then did is did a connection between the GNSS site and the tide gauge with leveling. And what you can see here is that the tide gauge is following the same trend as the GNSS site. So this tells us that the impacts that we saw at the GNSS site were also being seen at the tide gauge. So if we think about, if you look at where my hands are, if the GNSS site was here and the tide gauge is here, that piece of land has continued to subside at the same rate together. So there's nothing localized going on across that relatively about 2 kilometers. It's all moving downwards together. And to show you a summary of what we've done, it's hard to see, but you'll have the slides later. The numbers, you look at the ones in red, what we're seeing is that in Samoa and Tonga in particular, Samoa is subsiding at minus 7.8 millimeters per year since 2010. And I've got the uncertainties on there. The uncertainty on that is about 2.2 millimeters per year. So this means these results are statistically significant. This is actually happening. In Tonga, it's subsiding at 7.2 millimeters per year. Solomon Islands, which is slightly to the west, is subsiding at 2.4 millimeters per year. And PNG, the site we have there, is subsiding at 2.2 millimeters per year. So you can see that not all the countries in the Pacific are dealing with the same circumstances. And in fact, Vanuatu is rising. So Vanuatu is coming out of the water at about 3.5 millimeters per year. So this is a very complex region in terms of plate tectonics. And when earthquakes occur or other plate tectonic activity occurs, each country is seeing different effects. So the only way that we can address this problem of trying to understand sea level rise and the impacts of sea level rise is with good information. And we only have this at one site in each of these Pacific Island countries at the moment. But this work that's being done by the Bureau of Meteorology, Secretariat of the Pacific Community, with assistance from Geoscience Australia, is often seen as being some of the best information that's feeding into the International Panel on Climate Change reports, because it's a rigorous assessment of land motion with respect to sea level. So it actually tells us what is caused by land motion and what is being caused by climate change in this region, which really helps us understand how to best mitigate the impacts of climate change in those regions. So this is a good way of being able to explain geodesy in particular to your decision makers in your countries, to show them that geodesy is providing very strong foundations on which better decisions can be made. And that's definitely happening within this Pacific Islands region. So I'm happy to stop there and just see if anyone's got any questions, or I'm also interested in hearing about other people's challenges or experiences with joining land and sea data in your countries, and where we could potentially help you to try and make those connections and understand things better. Thank you.
Thank you, Nikki, for a good presentation. But we had the same problem in Tanzania, but we came up and realized that even with the monument, the GPS, which was almost about a few meters from the structure itself was deforming. Therefore, what I'm saying here is we don't only depend on the monument, which is a little far from the tide, but the tide monument itself may be deforming, and you may get maybe erroneous when you determine the tide. Thank you.
And that's why this information is so important. So this is telling us after we've done the leveling, this is telling us the change in the ellipsoidal height of the tide gauge. So if you level, depending on how regularly you want to do it, if you know that platform is deforming, if you consistently level between the GNSS and the actual tide gauge reference point on the top, you can create a model of this and understand how it's deforming over time. So even if you're not in a position to try and strengthen that tide gauge platform, you can at least understand how it's moving, and then you can model out the effects of the movement of the platform. That's something we've had to do at a couple of stations where the platforms have been hit by a boat. You can see there's a drop or a change in the position of the tide gauge. If you're leveling between the GNSS site and the tide gauge, you can model that effect and remove it. I'll go to Aslam and then I'll come back here.
Yeah, thank you. In South Africa, we have a bit of a challenge in trying to define the, so we have a horizontal datum on land being Hartebeespoort 94 aligned to ITRF. But how to, we find it difficult to define the reference frame for coordinates in the ocean. The people are asking us, even if you say it's Hartebeespoort or ITRF, whatever, how do they realize it? Because there's no known points on the ocean to connect to. So practically, how do they demonstrate this? For example, when they do offshore diagrams, it becomes on land. It's easy to say I am on this datum because I've connected to a point on this datum on land. What does one do? Because you can say anything. Because how does one in the ocean demonstrate you on a reference frame if there's no practical way of connecting to that reference frame? Yeah, I hope you understand what I'm saying.
Is that for the offshore, we use GPS and also the SBASs. We use the mean sea level you level from land, tie that to your benchmark, and then it goes all the way. We use the tidal datums.
Thank you. That's exactly as I understood it. This is something for us as land lovers we struggle with, and it's taken me a long time to understand this. We are so offshore. They're using mean sea level as a reference point, and then with that they also have the mean dynamic topography to deal with. So you can be above or below mean sea level depending on the time of day. So they're using tide predictions, and the tide predictions are developed based on the tidal data they got from that tide gauge. And ideally, you would have about 20 years worth of data to create good tide predictions based on that Earth-Moon relationship. So they're using GPS to get their latitude and longitude, and then their height is the sea level based on the tide predictions with respect to the bathymetry.
So the height part I can understand. Sorry that I'm continuing the question, but
that's okay.
Just for clarity. So I kind of get the height part. It's the definition of the horizontal part, because you can't realize a coordinate at any level of accuracy in the ocean, and you're not able to connect to any point on land that makes sense. So like, what does one do? Do you just choose, okay, let's just the whole world just go on ITRF 2020, epoch, whatever. So I'm just trying to say practically, because we have to legislate this. In South Africa, we have to legislate offshore diagrams, especially for exploration. And legally speaking, if we say that your offshore diagram must be in a certain datum, they got to demonstrate how they have put themselves on that datum. That's the question.
Yeah, so just in answer to that one, that's mostly managed through the IHO, and the standard that they use for IHO is WGS84. If you look through a lot of their standards and policies, it's WGS84, recognizing that they don't need centimeter accuracy, and they don't need to point to a reference mark and say, this is where we are. They're relying on the integrity and trust they get out of WGS84 for positioning of the when they're offshore. Yeah. Did you have something to add?
Yeah. And also, I think when you go offshore, for the, let me say, positioning and also the danger to navigation, is more relaxed as you go. The measures, the IHO measures they put for surveys in the offshore is more relaxed as compared to when you're getting through the ports. And then different countries like the US, they get their mean waters like every year because they have the resources to do it. So for other countries, they use the lowest astronomical tide, which goes for, I think, around 28 years to get a concrete model. But if your country is able, they use the yearly tidal datums if they want to.
Yeah, thank you. Sorry, I'll just go to the back and then I'll come to you, okay?
Thank you, Nick. We were having a conversation with Piwe at around breakfast about the research that has been done in South Africa, showing that there is actually, South Africa is rising. But Piwe quickly rectified that. He said it's not actually that South Africa is rising because it would affect the whole of Southern Africa. The fact is actually the sea level is actually subsiding. That is the exciting conversations we've had around around that topic of joining land and sea. Thank you.
Thank you very much. I'm sorry I wasn't there. Yes.
Merci beaucoup.
Thank you very much, Mick, for the presentation. I'll start with a question related to the presentation earlier. Why not install this permanent station directly? But then, for example, where you have countries where you have certain centimeters or meters will make a big difference. Why not combine a kind of co-localized site between the permanent station? Then the comment is with regards to the question from Aslam on the positioning of the reference systems. If you strive to look at the reference system, it's quite difficult. Here we don't have reference points, and sometimes you don't have access to solutions. One of the solutions could be to use the PPP, which will then link to the L-band. And there I think that could be an alternative. Of course, we'll be in phase with the national referencing, therefore the importance of modernizing our geodetic referencing systems, because if we have ancient systems and you have PPRTK, then we have to have different adjustments to ensure that our positions in the high seas is defined according to the national referencing system. But here we don't have this obligation. I think with PPT-RDK, we can have greater levels of accuracy. Thank you.
Yeah, thanks. I understand your second point, and I agree. And I think it goes to what Victoria was saying as well around relaxing the accuracy requirements. It makes those global systems like precise point positioning or for offshore as a good solution. With respect to your first question, it's an excellent option. There are some countries who have co-located sites. They have a tide gauge with a GPS mounted on the top, and then you can do everything all in one location. The reason that wasn't done for this particular study is because we felt that having something on the land, a GNSS site on the land, embedded into bedrock or very strong rock was going to give us a more accurate and reliable result. So that combined with leveling, we have found we can get millimeter accurate results. Whereas if you have a tide gauge, a GNSS station that's mounted on a tide gauge, you can get more movement from the platform, as we heard. You can also get more multipath effects from the ocean. So we're worried that we're going to degrade the signal of the GNSS. So it would still work, but you can't do it as accurately as if you have a station on the land embedded into bedrock. Yeah, but great point. And there are a lot of people doing the kind of work you suggest. Any further comments or questions